तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Now, we will analyze MOSFET differential amplifier. As far as the evolution of the differential amplifier is concerned, it follows the same lines as that of the BJT, right. And we can also conclude same thing about its gain. It is also equal to minus GM into RD. So, there is no difference, except that in the last signal, right, it behaves differently. Let us see therefore how. Okay. So, as far as small signal this thing is concerned, its gain is the same, G minus GM into RD, and input impedance is infinity, of course. Now, in the last signal situation, let us see how it differs. VID in this case, the differential signal, only when differential signal is applied we want to analyze this. When common mode signal is applied, once again the gain is exactly similar, that is, it is dependent upon RD by, let us call this as RS instead of RE. Okay. So, RD and RS ratios, right. So, exactly similar lines, you can split it into two separate, okay, blocks and evaluate it as RD by 2 RS minus RD by 2 RS. So, VID now is equal to, for last signal, VGS1 instantaneous value minus VGS2 instantaneous value, VGS1 minus VGS2. Next, we know that we will go from here, I VDD minus ID1 into RD, this is RD, this also is RD, equals VD1, okay, at this point. Similarly, VDD minus ID2 RD is equal to VD2 at an instant of time, and B naught is equal to, okay, VD2, okay, VD1 minus VD2, okay, as defined here, which will be nothing but, let us see, it is ID2 minus ID1 into RD from these two equations. VD1 minus VD2 is ID2 minus ID1 into RD. So, we have ID2 minus ID1 equals V naught by RD, an important equation. And what is ID2 plus ID1? Look at it, ID2 plus ID1 is equal to, we will call this again on similar lines as the BJT differential amplifier as I naught. So, from these two equations we can write down ID2 as equal to, add these two, okay, I naught by 2 plus V naught by 2 RD. Is this clear? 2 ID2 is this plus this. Okay, so ID2 is this plus that by 2. Okay, and ID1 equals, subtract this, okay, this from this, you get 2 ID1. So, I naught by 2 minus V naught by 2 RD. So, we got ID1 and ID2 in terms of V naught and I naught. Okay. Now, ID1 is also known to be equal to, okay, K into VGS1 minus VT whole squared, or from which we get VGS1 as root of ID1 by K plus VT. Similarly, VGS2 is root of ID2 by K plus VT. Therefore, VGS1 minus VGS2, which is defined as VID, VGS1 minus VGS2 defined as VD, is nothing but root of ID1 minus root of ID2 by root K. Okay. So, now ID1 and ID2 you substitute from that, you get this, okay, as ID1 was I naught by 2 minus V naught by 2 RD, okay, minus I naught by 2 plus V naught by 2 RD, the whole thing divided by root K is VID. So, this is giving you VID as a function of V naught, but we want V naught as a function of VID. Okay. So, we can actually now see that root K into VID whole square, I take this onto this side and square the whole thing. This is equal to, okay, this minus this whole square, which is I naught by 2 minus V naught by 2 RD, okay, plus I naught by 2 plus V naught by 2 RD, okay, this square plus this square minus, okay, this into this, right, okay, this into this, that is root of, okay, I naught squared by 4 minus V naught squared by 4 RD squared, okay, this into 2, okay, this whole thing, okay, is equal to K into VID squared, this square. Is this clear? So, this I naught by 2 and this whole thing simplifies to simply I naught. Or we get I naught, okay, minus K times VID squared, okay, equals, okay, to root I naught squared by 4 minus V naught squared by 4 RD squared. Okay, now what do? We have to square once again I naught, okay, we will take this as squared plus K squared VID to the power 4 minus 2K VID squared I naught. This is going to be equal to 4 times I naught squared by 4 minus V naught squared by 4 RD squared. Clear? So, now you have this getting cancelled with this. This is I naught squared, that is I naught squared, and we get this as minus V naught squared by 4 RD squared. 4 gets cancelled. Okay. So, we make this plus, right, or we want V naught. So, V naught by RD, root of that, we take root of this. If you take root of this, you have VID squared VID to the power 4 here. So, VID we get, okay, and we will take actually the whole thing out, okay, 2k root of 2k into I naught. When I am taking the root, I naught 2k root of that into VID to 1, okay, root of 1 minus, okay, I have taken out VID squared. So, we get VID squared remaining there, right. I have taken out k, so k remains there. I have taken out 2, so it will be divided by 2. I have taken out I naught divided by I naught. Is it clear? Please check that. So, this is the relationship between input and output, okay, V naught into this. So, V naught is equal to RD, okay, into VID, okay, root of this to that, square root. It could be plus or minus, okay. So, it is strictly speaking minus, because that is a phase shift of, okay, 180 degree as we have assumed the polarity. So, this factor, if you verify, minus RD VID root of 2k into I naught, if you verify, please verify, okay, this factor root of 2k I naught is nothing but what? The GM, right. If you verify, right, the GM of the whole thing will be this, right, GM into RD. Each of the FETs will be operating at I naught by 2, okay. So, the operating current of the FET will be I naught by 2, and from which we can obtain the GM of the FET from its characteristic, right. So, you will see that this is nothing but GM minus GM into RD into VID, which is the small signal gain. Apart from that, we have a non-linearity coming into picture. In order that it is perfectly linear, now we get an important factor regarding distortion. K into VID squared divided by 2 I naught should be much less than 1. So, K into VID squared divided by 2 I naught should be much less than 1. This is going to be small signal, then it is perfectly linear. So, now like we had got in the case of differential amplifier using BJTs, we got Vp squared, okay, divided by 96 Vt squared or something like that, much less than 1. Similar to that, we have got a condition here, but here please remember we have not yet obtained the harmonic distortion. This is only it is square root of 1 minus this kind of thing. If this factor is much less than 1, then I can make certain approximations. Okay. What are those approximations? If this factor is much less than 1, the square root can be approximated as, you know mathematics, 1 minus, if this 1 minus square root of 1 minus x and x is small, what is square root of 1 minus x? 1 minus x by 2. Okay. So, square root of this, therefore, approximation under this assumption V naught is equal to minus R d root of 2 k I naught into V I d into 1 minus k V I d squared divided by 4 I naught. Square root is gone. Okay. Now, what is the nonlinearity existing? Again, you can notice something. This is V I d and there is V I d cube. So, if you go for only sort of amplifier using, let us say, common source amplifier, instead of common emitter using MOSFET, you go for common source, the nonlinearity will be square nonlinearity. The second harmonic is the first component, in fact, the only component that comes into picture for distortion, but it is going to be dominant. Here in the differential amplifier, you see that the harmonic component is what? Third harmonic, like in the case of bipolar junction transistor. Now, in this V naught is equal to minus R d into this factor is nothing but G m, and this is V I d. So, this is what happens to the signal, linear part of the signal component. This into 1 minus k times V I d squared by 4 I naught. So, now suppose V I d is taken as V p sin omega t, then what happens? Let us see. So, we have the fundamental component coming as minus R d G m into V p sin omega t, that is clear. So, now what is the component corresponding to the other part? Minus R d G m. Now, we will take this V p inside sin omega t. So, we get k into V p cube sin cube omega t by 4 I naught. Now, sin cubed omega t, yesterday also we had converted into 3 sin omega t minus sin 3 omega t by 4. Right. So, we can now see that this 4 combined with this, we get 16. So, the third harmonic component is going to be k V p squared divided by 16 I naught as against V p of the fundamental. G m R d is a common factor for both. So, let us do the same thing that we did earlier. So, the fundamental component will be minus G m R d into V p, p component of the fundamental, right, and this one the harmonic, right, percentage or ratio of the distortion is going to be again minus G m R d into V p k V p squared by 16 I naught. Is this clear? So, you can see now that this k V p squared by 16 I naught should be kept at whatever value you want, 1%, this means 1 over 100. That will give you the value of maximum value of V p for which it can be used. Now, I want you to work out the same problem that you worked out with BJT differential amplifier compared with BJT common emitter amplifier. Here compare common source amplifier which has square law distortion coming into picture at the output and second harmonic component coming at the output. Okay. Find out the VP required for 1% distortion at the output in both the cases and compare these, and you will definitely see that differential amplifier is far superior to the common source amplifier. So, distortion wise this amplifier is definitely superior, and therefore, again we will never go for such common source amplifiers as discrete stages. We will go for the differential amplifier because it has superior large signal property. Now, as far as the current switching etc. that we discussed in the earlier situation is concerned, here also it is valid. The current gets completely switched over to this when VID is positive, okay, and large, and current gets completely switched over to this, okay, when VID is negative and large, and therefore, the output voltage swing is again equal to twice I naught into RD. So, basically except for the nonlinearity, right, the rest of the things remain the same. This output swing is once again obtained only when these transistors do not go to the triode region, okay, when the full current is flowing through these. Okay. Just like BJT not going to saturation when the full current is flowing through this, only under this assumption we have this full swing of, okay, 2 I naught RD peak to peak, okay, symmetric swing because of the differential signal. Now, as far as common mode operation is concerned, again this same thing is valid, that if I short this, no VID is there, then there will not be much of a change that is going to occur here. This voltage can keep on rising until this voltage, which is drain to gate voltage, becomes equal to minus VT, right, until the drain to gate voltage becomes equal to minus VT, at which point of time it is entering the triode region. So, that will be the limiting common mode signal, upper limit on common mode signal that you can apply to this differential amplifier. On the lower side, obviously it can go on until I naught becomes equal to 0, right. So, these are the signal limitations of the differential amplifier both for common mode and differential mode. When both of them are coexisting, obviously the voltage here, the minimum voltage here is likely to be VDD minus I naught into RD, and that will set up a limit on this. Okay. Just as we had discussed offset voltages in BJT differential amplifiers, let us also consider offset voltages in MOS differential amplifier. Now, in the last class when we discussed the offset in BJT, what we said was there is an output offset voltage, and that is very easily defined as voltage is that voltage, okay, that appears at the output when input is made 0. So, VID is 0. Okay. Under that situation, why would output have an offset? Obviously, ID1, okay, is not equal to ID2, because ID1, okay, is equal to K times, okay, VGS minus VT, and this VGS, because as far as the MOSFET is concerned now, input is grounded and the sources are connected together, both the inputs are grounded, sources are connected together. So, what happens, VGS will be the same for both, VGS1 is same as VGS2. So, VGS1 is equal to VGS2 is equal to VGS under this situation. So, this is K times VGS minus VT whole squared. ID2 is also K times VGS minus VT whole squared, but they are not identical. They can have the K as K1 and K2, and of course, VTs also can be VT1 and VT2, but we are assuming that the threshold voltages are same, and threshold voltages are process dependent, and this is process dependent as well as geometry bit dependent. We are assuming that there is a mismatch only in geometry. So, K1 and K2. So, then we know that ID1 is different from ID2. So, V0 is simply ID2 V0 offset ID2 minus ID1 into RD according to us. Therefore, this is equal to, we have here K1 ID1 ID2 minus K2 minus K1 into VGS minus VT whole square into RD. So, it is the mismatch factor which is responsible for the output offset, and VGS minus VT whole square is nothing but ID1 by K. So, we can put this as ID1 by K. And what is ID1? ID1, since these are right, is going to be very nearly equal to I0 by 2, right. It is going to be slightly different because of the fact that K1 is going to be different from K2. So, ID1 by K into RD K1 ID1 by K1 or ID2 by K2 is equal to this. So, this is the output offset. Is it clear? Now, in a good differential amplifier, ID1 will be very nearly equal to ID2 will be very nearly equal to I0 by 2 nominally, but they will be different because of the fact that K1 is slightly different from K2. So, in this expression, therefore, you can put ID1 as I0 by 2 and this K1 very nearly equal to K2. Fine. What about input offset? Now, as far as input offset is concerned, what is the basic definition? It is that voltage that I have to apply at the input in order to make the output equal to 0. That means, under this situation of K1 being different from K2, I am making ID1 equal to ID2. If I make ID1 equal to ID2, output voltage will be, offset voltage will be 0. So, ID1 is made equal to ID2 equal to I0 by 2. Under this situation, right, what is going to be the ID1 is going to be equal to ID2. We are not interested in this factor, this is very near. ID1 is equal to ID2. Under this situation, we have K1 into VGS1 minus VT whole squared equal to ID1, or VGS1 is equal to root of ID1 by K1 plus VT. VGS2 is equal to root of ID2 by K2 plus VT. So, VGS1 minus VGS2 is the VID, input offset. This is the input offset voltage when ID1 is equal to ID2. Okay. So, we have this equal to root of ID1 or ID2, which are both are same, into 1 by K1 minus 1 by K2 root of K1 root of K2. This is the what? This is the input offset voltage. Here, please note that we had assumed K1 and K2 to be different. This could have resulted in the input offset could have resulted also because of VT1 and VT2 being different. That means this plus VT1 minus VT2 is going to be the further addition to this input offset. This is what you should bear in mind, and therefore, because of such uncertainties in these two parameters, typically a MOSFET differential amplifier has about 20 millivolts offset voltage, as against what did we get for BJT of the order of 1 to 2 millivolts. So, an order of magnitude higher input offset voltage for MOSFET. This is to be borne in mind by a design engineer, because we will therefore never use a MOSFET as a differential amplifier stage at the input of any amplifier if offset has to be reduced. Okay. Obviously, this is what is called delta VGS offset, because primarily it comes because of VGS being different for the same current. This is called delta VGS offset, as against in BJTs it is called delta VBE offset. So, this is of the order of 20 millivolts as against 2 millivolts in BJT. So, at any time you can say therefore that as far as delta VB or delta VGS offset is concerned, the BJT is the one to be selected. And also in this I said, if you go for higher input impedance by pairing Darlington transistors as differential pairs, then the uncertainty here will go to double. Instead of 2 millivolts it will become 4. If you use 3 such transistors, it will become 6 millivolts. Even though the beta is progressively increasing and the base current is progressively decreasing for the same, or input impedance is progressively increasing. This is the configuration with the highest input impedance, infinity, right? And there you have maximum offset. This is the case with any amplifier configuration. If you try to increase the input impedance, input offset will increase, right? There is always a price that you pay somewhere or other. So, when you try to increase input impedance by any means, right, the input offset voltage will increase. This is a serious problem, particularly in DC amplifiers or low frequency amplifiers. So, where the input offset is of no consideration, where other offset voltages are more dominant, there you can use MOSFET differential amplifier. Now, what are the other offsets that can come about is what I would like to discuss in the few minutes that are left. First, consider the bipolar transistor. Now, this is what is called delta VB offset. When both the bases are connected together, VVs are the same. At that point, the two currents are different. Now, you can have, apart from this, because of finite base current and finite base resistance, that you are putting some base resistance, let us say RB1, RB2 in your circuit. That means it is not grounded straight, it is grounded through a DC resistance of RB1 and RB2 through the respective bases. In such a situation, in this case you have what is called IB1, and in this case you have IB2 flowing. So, this will develop a voltage of IB1 into RB1, and that will develop a voltage of IB2 into RB2. The differential voltage applied to the base now is IB1 RB1 minus IB2 RB2, right. This is the differential voltage. Okay. If IB1 is same as IB2, RB1 is same as RB2, this voltage is 0. Okay. So, RB1 should be same as RB2, IB1 should be same as IB2. RB1 and RB2 are external resistances that are put. So, even if IB1 and IB2 are not equal, we can make these resistances, okay, such a way that this whole difference is equal to 0. This kind of offset, okay, is called bias current input, bias current offset. That means this arises whenever IB1 is not equal to IB2. This can happen because even if these two currents are the same, because the betas are drastically different. Alphas may be very nearly equal to 1. One alpha may be 0.995, another alpha may be 0.994. Okay? That means alphas are very nearly the same, but betas can be now drastically different, and therefore these two base currents may be different, okay, for the same matched pair. Base currents may be different because betas are, okay, going to be different, and therefore the bias current flowing through the different base resistances through this will create an offset, and this is an important design requirement, that if you are worried about bias current flowing to resistors, this bias current may be very low, that depends upon the value of beta. It will become still lower when we use a Darlington pair. Okay? So, that means using Darlington pair or using MOSFET or JFET will make this bias current offset progressively come down. It is very bad in the case of a single pair of transistor. So, the bias current offset is a serious problem, okay, in the case of a BJT and when it is a single pair. It is of no concern when it is a MOSFET because bias current is almost 0. So, it is almost non-existent in the case of a MOSFET. So, if you have sources coming with large resistances at the inputs, which might therefore cause bias current offset, then you will use MOSFET as input stage. But if you are sure of sources with low valued resistances coming at the input, okay, where the bias current offset is going to be extremely small because the impedance RB1 and RB2 are going to be very low, then you will use bipolar junction transistor. So, application depends upon the source that you are going to choose for your application, right. So, this amplifier, what it is going to be, whether it is going to be MOSFET input or BJT input, depends upon the source impedance, okay, and whether it is a low frequency application or not. So, this is an important aspect about offset. The total offset is going to be bias current offset plus delta VGS offset or delta VBE offset. And the voltage may be able to drift either because of bias current offset voltage or because of delta VBE or delta VGS offset or both. Okay. Let us now work out an example using this MOSFET differential amplifier. Example 15. Determine the following for the MOSFET differential amplifier shown biased at I naught equal to 2 milliampere. The MOSFET differential amplifier is shown here, T1, T2. It's biased at I naught equal to 2 milliamperes. If it is 2 milliamperes here, then we know that this current and this current being equal will be equal to 1 milliampere each. So, we know that IDSQ is equal to 1 milliampere is equal to K into, which is 1 milliampere per volt squared into VGSQ minus VT whole squared. So, this is 1. So, VGSQ is equal to 2 volts from this. 2 minus 1 is 1 equal to 1. So, we get from this relationship that VGSQ here becomes 2 volts each. So, this is plus, this is minus, this is plus, this is minus, this is 2 volts, this is minus 10 volts. So, the drop across this is 8 volts. We want to have 2 milliamperes through that, and 8 volts is the drop across it, and therefore, R is equal to 8 volts divided by 2 milliamperes, which is equal to 4 kilo ohms. So, we get the value of R required to bias this at 2 milliamperes as equal to 4 kilo ohms. Now, we are in business. We can first find out the operating point of the transistors. This is already given as 1 milliampere because this is 2 milliamperes. So, the voltage here is going to be a drop of 5 volts. 1 milliampere into 5 K is 5 volts. So, this is 10 volts. So, this voltage is 5 volts, this is 5 volts. So, VDGQ is 5 volts and IDSQ is already given as 1 milliampere. So, this is the operating point. Then we want the differential mode gain. We would like to now find out the GM of the FET. GM is equal to, we know that it is 2K into VGSQ minus VT, because IDSQ is equal to K into VGSQ minus VT whole square. Differentiating it, delta ID by delta VGS comes as 2K into VGSQ minus VT. Okay. That is VGSQ minus VT into K, this whole square is equal to IDSQ. So, strictly speaking, in this case IDSQ is always equal to I naught by 2 for the differential amplifier. So, I would like to express GM of a differential amplifier in terms of I naught. So, IDSQ is always equal to I naught by 2 for differential amplifier. That means VGSQ minus VT is equal to root of I naught by 2K from this always. Therefore, GM of the differential amplifier is equal to 2K into root of I naught by 2K, which is always equal to I naught into 2K. So, this earlier also I have mentioned, we have substituted for GM root of I naught into 2K. Given I naught as 2 milliamperes and K as 1 milliampere per volt square, we have GM equal to root of I naught, this is 2 milliamperes into 2 K, which is milliampere per volt squared, we get 2 millisiemens as the GM of the differential amplifier. So, the gain of the differential amplifier is simply GM into RD. This we had established, minus GM into RD. This is the differential mode gain. So, this is equal to minus 2 into RD is 5K. So, this is minus 10. So, this is the differential mode gain. single ended output, this is equal to minus 5. It is minus Gm into Rd by 2. So, the B part is over, differential mode gain. Now, we have to discuss about common mode gain. So, common mode gain also we can replace the whole thing by its equivalent circuit and do it, and we can show that it is similar to what we obtained in the case of a bipolar junction transistor. So, one way is you can replace the whole thing by its equivalent circuit phi k. This is connected to ground, and you have the Gm into Vgs, and we are having it at the source, and from the source we have to the ground a resistance of now 2R. R is already known as 4K, so 2R is equal to 8K. So, this is the ground, G is 2, right. So, this is the equivalent circuit that we have to solve. Okay. So, we would like to now find out the output here, okay, and through the output we have this current flowing Gm into Vgs. So, Gm into Vgs into phi k is the output, okay, that divided by the input. Now, this is actually the same current is going to flow through this particular thing, and therefore, the Vgs, okay, is going to be the input, right. So, actually speaking, we are going to apply a voltage here from this point to ground, which is the common mode voltage, right. So, the input is going to be Vgs, which is Vc, okay, minus Gm Vgs, Gm into Vg, yes, because this is going to develop a potential like this. So, into 8K, this is the Vgs here. Vgs is Vc minus the drop here Gm Vgs into 8K. So, output is, okay, V naught is equal to Gm Vgs into phi k. So, we can actually eliminate Vgs from this and obtain Vc divided by, that is V naught divided by Vc as the common mode gain. So, Vgs is equal to Vc minus Gm Vgs 8K, that means Vgs into Gm is already given as 2 millisiemens. So, this is going to be 2 into 8K. 2 into 8K is 16. So, Vgs into 17, okay, is equal to Vc. So, we have got Vc in terms of Vgs. So, we substitute it there, V naught is equal to Gm Vgs into phi k, right. So, Gm Vgs into phi k, right. So, this is Gm into Vgs is going to be equal to 10, okay. Vgs, Gm into Vgs is 2 into Vgs into phi k, so 10. So, 10 Vgs divided by, okay, Vc, which is 17 Vgs. So, you can see that the common mode gain is 10 by 17. So, common mode dejection ratio CMRR is AD by AC, which is equal to 5 divided by 10 by 17, or this is 8.5. So, we have now worked out for this differential amplifier all these, the operating point of the transistor, differential mode gain, common mode gain, and CMRR.